When matter is compressed into a state where its density precludes the escape of all signals, a black hole forms. While the most common examples are the remnants of massive stars, new observations suggest their origins are far more diverse than the death of a single sun. Theoretical exploration began in 1939 when J. Robert Oppenheimer and Hartland Snyder modeled the gravitational collapse of a uniform, pressureless ball of dust. Their work focused on the Schwarzschild radius, a specific volume threshold where a mass becomes so compact that its escape velocity exceeds the speed of light. At this point, as shown in this diagram, the region is cut off from the rest of the universe. While Oppenheimer's model relied on perfect spherical symmetry, Roger Penrose later proved that black hole formation is a robust consequence of general relativity. He introduced the trapped surface, where all light rays are forced to converge toward a central singularity regardless of the star's rotation or asymmetrical shape. This established that black holes are physical objects that should form in the real universe whenever matter is sufficiently compressed, rather than being mathematical artifacts of idealized equations. In the modern universe, that compression occurs during the life cycle of stars, at least 8 times more massive than our Sun. These stars exist in a state of hydrostatic equilibrium, balancing the inward pull of gravity against the outward pressure of nuclear fusion. This balance fails during the iron crisis. As seen in this cross-section, the star fuses heavier elements until it reaches iron. Because fusing iron consumes energy rather than releasing it, the core loses its outward pressure support, leading to a catastrophic collapse. Gravity must then overcome 2 quantum barriers. First is the Chandrasekhar limit, where electron degeneracy fails, followed by the Tolman-Oppenheimer-Volkoff limit, the point where even neutron degeneracy cannot halt the contraction. Once these limits are exceeded, the core collapses in a fraction of a second. While a successful supernova shockwave might leave a neutron star behind, a failed explosion or mass fallback crushes the remnant into a stellar mass black hole. This process explains the black holes we observe locally, but it struggles to account for the massive objects found in the early universe, or the specific gaps in the cosmic mass distribution. For helium cores between 65 and 130 solar masses, extreme temperatures convert gamma rays into electron-positron pairs, sapping thermal energy. The pressure drop triggers a violent oxygen and silicon thermonuclear explosion, completely disrupting the star. Leaving no remnant, this creates a black hole mass gap. However, gravitational wave detectors like LIGO have observed black holes exactly within this forbidden range, such as the 142 solar mass remnant of the GW190521 merger. The explanation lies in hierarchical merging. In dense environments like globular clusters, black holes can collide and merge multiple times. These second-generation objects can grow into the mass gap and eventually form intermediate mass black holes. This shows that when stellar evolution cannot produce a black hole, dynamical interactions in crowded clusters can bridge the gap through violent multi-stage collisions. The scale of the problem increases in the deep universe. We see supermassive black holes existing a few 100 million years after the Big Bang, too early to have grown to such sizes through the death and slow accretion of ordinary stars. This suggests heavy seeds. Massive primordial gas clouds collapse monolithically into seeds up to 100,000 solar masses, bypassing star formation. This direct collapse requires rapid angular momentum loss. Global instabilities form bars within bars, funneling gas inward through secondary bars straight to the center. The James Webb Space Telescope has identified early galaxies that appear overmassive, hosting black holes far larger than local relations would predict. This includes LID 568, which is accreting matter at 40 times its theoretical limit. These feasting episodes of super-Eddington accretion allow seeds to grow rapidly, explaining how they became large enough to anchor the very first galaxies. Observations suggest that in the early universe, black hole formation was a primary driver of galaxy structure, rather than a passive endpoint of stellar life. The earliest potential formation channel dates back to less than 1 second after the Big Bang, during the radiation-dominated era of cosmic inflation. During this period, quantum fluctuations created localized regions of extreme density. If a fluctuation entered the horizon with enough amplitude, as shown in this topographic grid, The gravity of that region would overcome the expansion of space and collapse into a primordial black hole. While the smallest of these primordial black holes would have evaporated by now through Hawking radiation, larger ones would remain stable. Because these surviving relics are stable and non-baryonic, they are a candidate for dark matter, potentially providing the invisible gravitational mass that holds galaxies together today. This suggests that some black holes are not products of matter within the universe, but are features created by the conditions of the universe's birth. These formation channels range from the quantum fluctuations of the infant universe to the collapse of massive primordial clouds and the eventual explosive deaths of massive stars. Future missions like the LISA Space Observatory will detect the mergers of the supermassive giants, allowing us to trace how these initial seeds evolved over billions of years. Furthermore, if ground-based detectors find a sub-solar mass black hole, an object too small for any stellar process to create, it will provide definitive proof that primordial black holes exist. By identifying which of these mechanisms dominate across different eras, we can better account for the mass distribution in star clusters and the rapid growth of the very first galaxies.